All right, thank you all for reconvening after a short break, and we'll have a longer break in roughly 45 minutes or so. It's my pleasure today to introduce one of our EMDL co-investigators, the lead from the Colorado School of Mines, Professor Dorit Hammerling, who's in the Department of Applied Mathematics and Statistics. And we had a bit of an introduction to the statistics from the last panel. And so Dorit is going to be talking about her work on continuous monitoring systems. Dorit.
I'm the fourth partner in crime of the creation here, just to say that. And yep, are we good on go? Yep, I was just going to say I'm fourth partner in crime in creating this. And yeah, I did not ask Matt to give such a nice introduction why there's so many statistical problems. Oh, okay.
I don't know, did it? Yeah. Well,
you want to try again?
Should be.
Can you hear me now? Is it good? Good, all right. All right, well, all that to say, it was great to get such a good introduction from Matt. Clearly, there's a lot of statistical problems involved here. I've only worked on methane for the last 3 years. I want to very briefly mention some other projects I used to work on, namely making cement plants run cleaner with less CO2, where we have hundreds of sensors. And then I worked with NASA on looking at CO2 from space for 5 years. And lately on climate models at the National Center for Atmospheric Research and getting things right there. And all that to say, I actually feel this problem is pretty tangible because we have a lot of really smart people working on it and we have resources. So maybe from my perspective, and only working on this for the last 3 years, this is actually something I think we have a real chance of making a huge difference. And exciting thing about being a statistician, we can pick these projects and work with all of you on something very exciting. So I'm going to talk about something very specific we have been doing, namely using these continuous monitoring systems in constructing measurement-informed inventories. And to put that a little bit in context, so Matt has come up with these examples for the whole basin here. Here we're really looking at the facility level here. And just iterating that again, obviously, it's very clear, I think the work we have done, and this is a speaker from the QMV project, we really need these multi-scale measurements because these processes we are trying to detect, they work on such different scales here. So continuous monitoring systems, I've highlighted two aspects here where I think they have a real niche. One is detecting these very subtle shifts. I'm not going to talk about this today, but just to mention very briefly, if you want to look at things like we swapped our pneumatics, that's what we can actually see on very clean sites with this continuous monitoring system. But the other topic that I'm going to focus on today here, specifically, do I have a laser pointer here, is talking about this high temporal intermittency. So these are the kind of processes here that I'm giving you an example here. These are 3 months of simulated data, but this is very analogous to a lot of data we see in emissions from facilities where you have most of the time not much is happening, but occasionally we have relatively high emissions here. And here you kind of see a zoom in of what that would look like roughly over a day here. And for these kind of data, so what I did here as a demonstration here is you see a histogram of all the data I showed you from these 3 months here. And you see what the true mean here is. So roughly 15 kilograms an hour. Now we are taking a sample. So this is a sample of 15 measurements. So let's say that would compare to 5 measurements you take a month. So that's a relatively high number here. We have a sample mean here that looks like this. That's 6 kilograms. So there's a big difference to what the true mean is. Next sample we pick, and these are just samples we picked. There's nothing that I constructed here. 45. Next sample we pick, back to 4 here. So this is a summary here of what that actually looks like. So we're only looking at what's the effect of the sample frequency in estimating the mean from these samples compared to what the true mean here is. So the red line would be if everything is the same. So in the red line, I would say our sample mean here corresponds directly to, sorry, the pointer doesn't work great, corresponds directly to our true mean here. And you can see how that varies, that distribution, as a function of how often we sample here. And if you have a zoom in here, so we are zooming in on that black box here, you can really see if we don't sample very much and we have underlying data that's very critical here that has these very skewed distributions, you see there's a lot. We are often far off of what the true sample mean is here. And you can particularly see that in these lower frequency samples, we actually underestimate most of the time. Sometimes we radically overestimate, but mostly we slightly underestimate. So in these kind of cases, you really want to have basically your eyes on the ground and try to really have frequent samples or inference on what the emissions are. That, as a setting by, in some cases, using continuous monitors is really critical. One aspect about continuous monitors, and I think that fits very well with all these discussions we had about measurement uncertainties, continuous monitors, I'm very specifically talking about this kind of point-in-space monitors, they don't directly measure what we actually care about. And that's something to really establish as part of the issue why this is somewhat tricky here. So we measure concentrations with continuous monitors, but what we typically care about is emissions. So we are seeing concentrations that result from emissions. And in mathematical terms, the kind of problem we have here is an inverse problem. That means we want to use all these concentration measures to then infer what are the emissions here. And here's a little animation that I think in various forms we have seen before. So the red triangle here is an emission source, and then we have sensors placed around it. And this is about as simple as a scenario as we can get, right? There's nothing happening, there's no obstacles, nothing else. And what you see here on the left, that's now the concentration data resulting from these emissions. This is real wind data, nothing made up. So this is exactly the kind of data we work with in these continuous monitoring scenarios. And we're saying now, we want, from these data, we want to know, A, is there really something going on here that is at that site and not from the CAFO that Dan mentioned before next door? Where is that red triangle? That could be on different sources here, and how much is it emitting? So just to state clearly what the problem is. Obviously, the people working with continuous monitoring, they are very aware of that, but I think it's worth pointing that out so we remember what we actually mean when we talk about uncertainties in these kind of settings where we infer emission rates here. So we have come up at the Colorado School of Mines with one framework here. I'm not going into any technical details. We are more than happy to send you the paper on all this, but I'm going to very briefly describe it. So first step is figuring out, is there actually something going on? Which comes back to this background removal, which in many cases, especially if you have CAFOs or other sites next to it, is actually a non-trivial question. The second step here, that's what we write here, simulation, that's that step in the inverse model. We have to actually link what you see in concentration space to what is the potential emission source. This is a critical part I'm going to talk a little bit more about because I think there's a lot of potential making that part better. And then figuring out what the localization is, so where is that source happening, and then the quantification. Again, not going into any details here. But the three things that are important about this framework is we are doing this completely open science. I think a lot of the development so far has happened a little bit behind closed doors for understandable reasons, but in our space in EEDML land, we do this open science, so anyone can use these kind of models. They're modular. So modular means if you come up with a better model here, let's say in this dispersion space that is the simulation part, we can plug it in. This is exactly open in the sense of we can improve things. And it's also sensor agnostic. Obviously, the quality of the sensor matters, in like how good is the actual precision and the accuracy on your sensor data, but overall, any kind of sensor can fit into this kind of work. So without going into any more details, this is the framework where I'll give you an example of how we use that on a real site as part of the QMRV program. Again, this is published work that you can read in more detail here. So this is a very simple production site. Only very few pieces of equipment can potentially leak here. And what we had there, so the way this program worked, and Fiji is going to talk about that longer, is we had these aerial measurements, and then the idea would be our job here, we were the independent verifiers, is looking at these aerial measurements that were taken over 4 days and saying something about how do they actually compare to the bottom-up inventory. And I think we had ample discussion here on they were quite different. So this is a specific scenario where our job was, well, if they are quite different, dig deep, what was actually going on. So we were lucky on that side that we had actually continuous monitoring data, and the company was very helpful and worked with us in detail in giving us all this data so we could actually dig deeper and play that game to see what's actually going on here. I want to say one more time, this is a very simple site. This kind of work is much, much harder if you would do this on more complex sites here. So an example here is, so we play that game that we do this inferential process here, and I'm showing you 1 week here just to give you an idea of what that actually looks like. So in this specific case, we run that framework every half an hour. So every half an hour, we use the data from all this continuous monitoring sensor and say, oops, what's actually happening? Was there something emitting? If so, what was it? What's our best estimate at estimating this? And these individual bubbles here is the best estimate with the lines around it, the uncertainties around it from our framework. And you can then tally this up and link that back to what would the monthly inventory actually be here. So for reference, I'm showing what the bottom-up inventory from the company is. This was a very, I would say, extremely diligent operator who did a very good job of documenting this and changing this for every month and all this kind of detail here. So in the individual colors matching here, these different equipment groups, and the gray is the overall site inventory here. And what we did now is using that framework I showed before to also calculate from the continuous monitors what would be the corresponding measurement-informed inventory here. And you can see here in the early months, October, November, December, not that much happening and so on here. But remember the bridge overflight was in April when we had something on the order of 12.5 kilograms per hour. We really saw a big change happening here. Here in February, the end of February, there was something happening. So we went back and talked to the operator, and there was a big equipment change without going into details, but clearly that was something the operator was very aware of, and we could very well capture that in this continuous monitoring estimates based on this, using this framework here. So to summarize all this, so the bottom-up inventory really did not capture this operational change, even though they followed all the rules one should follow. And the aerial measurement was really crucial. Had we not had that aerial measurement, we wouldn't even have bothered to look into any of this. The point is also, though, had we only that one aerial measurement, we would have also severely overestimated what was happening in earlier months. So this is a good example of that. And with that, here's a few references. This is all published work, and I would like to thank my research team. It sounds to me like they will not have any problems finding jobs from all we have heard here. Thank you.
Well, Dorit, let me ask one question. You referred at multiple points to, well, this is a simple site, and it could be a lot harder with complex sites. Can you talk a little bit, at least qualitatively, what makes a site complicated? Is it buoyant sources? Is it big structures? Is it all the above? What makes a site complicated?
Can I get the slides back, please? Thank you. It's only because I have such a good example here in my backup slide. This is the key problem in my thoughts here. On this, this is a nice visualization we stole from Project Canary on the webpage. But what makes sites complex is if you have a lot of things going on. Right now we use these really simple models that say, well, the wind blows this way. But in reality, on this site, you have multiple emission sources, and you have a bunch of obstacles in there. And we have models right now, all they think is this is what's happening. Clearly, we are very aware of that's too simple. And just cutting it off doesn't work either. So we have these really complicated full fluid dynamics models, but they don't run in real time. So what we are working on, and Riker back there really hard, is coming up with models that run really fast, but account for what's actually going on the site. And that's certainly not trivial.